This is a video demonstration of the new NeuroNavigator add-on and standalone program. The add-on is inside of NeuroGuide, which allows one to drill down inside the brain into a three-dimensional volume to look at the sources of the EEG and to evaluate and navigate through various parts of the brain, which I will be doing in a minute. This is a 12-year-old child that a neurologist, as part of a team at Massachusetts General Hospital and at Harvard, sent me data because they were trying to evaluate whether or not to do neurosurgery to remove the epileptic foci. This child had arterial malformation that resulted in the left hemisphere spike and wave that you can see here. You can see here this is P3 is much larger than, P3 is much larger than P4. In fact, there is no epileptic events in P4. There is in O1, but not in O2. There is in T3, but not T4, and in T5, but not T6. And essentially a left posterior inferior region that is epileptogenic. And so the evaluation that was given to me, and I'm going to drill down through this or scroll forward so one can see that there's no artifact, and you can see this is a continuous epileptic event. The data was sent to me to evaluate the healthy right hemisphere, to look at the conductivity, the phase differences, the conduction velocities, the current densities, the localization of power, etc., and compare it to a normative database, and she came up with fairly healthy right hemisphere, because this is quite a focal left hemisphere dysfunction or epileptogenic process. They decided at the end of the day not to do the neurosurgery because of her age at 12 years of age and because of her adaptability over the years of being able to adapt to this event with her compensatory right hemisphere. I'm going to click home to go home. And because the extent of the epileptic focus was so large that too much tissue would have to be removed, and which would interfere with the quality of life that she had before surgery. Now, there was a complete workup of her at Massachusetts General Hospital with 128 channel EEG, with PET scan, and with high-resolution MRI. And the neurosurgeons had a very good view or understanding of the extent of the epileptic foci. So my job was really not so much to deal with the neurological foundation of the epileptic foci, but rather the healthy right hemisphere. But for purposes of demonstrating the utility of the NeuroNavigator for raw score evaluation of gross neurological dysfunctions, such as this epileptogenic event, I'm demonstrating that here. Now, initially, what we want to do, and I've already selected data because it's quite artifact-free. There's a little bit of artifact eye movement, but very little. And I was able to remove that and not select it. In any case, I'm going to click View Dynamic FFT to look at the deviation from normal, at which frequencies are most deviant. That gives us an idea of when we go to the NeuroNavigator, which frequencies we'll select. You can see at 3 hertz, and then there's a harmonic at 6, roughly 5.56. And then there's this very large spike here, because it's an unusual event, actually, that's happening at these higher frequencies. We can also go to analysis or report and generate analysis to evaluate the distribution of scalp energies and in terms of the power of the EEG. And you can see it's quite focal in the left hemisphere. It's blue in the right because there's so little relative energy compared to the epileptic focus. And there's 25 hertz. Here's 40 hertz. You can see this fairly extensive because this is a sharp wave at these higher frequencies. And at 50 hertz, you can actually, it looks like there's 2 separate foci. It's more broad at the lower frequencies where the sharp waves are present at these regions. You can save this, of course, but now what I want to do is turn on the SW Loretta NeuroNavigator, and let's drill down and evaluate this epileptogenic event in the left hemisphere. I'm going to minimize the NeuroGuide. I'm going to click Analysis, NeuroNavigator. In this case, I'm going to click Raw Scores. I'm going to expand the NeuroNavigator screen and make some initial adjustments. This is a default, which just automatically comes up. You can see the transparent brain here. This is the electrical potential at the scalp surface, and this is S Loretta. It's actually SW Loretta. By S Loretta, we mean standardized Loretta. Standardized Loretta is a statistical method, essentially the same as used by functional MRI to transform voxels into a probabilistic evaluation. That is S Loretta, and same with functional MRI. What one does is divide the source space or the blood flow signal by the variance of the voxels. And so one takes multiple measures, gets the variance, divides the variance into the current source density in this case. And what this means is that if there's a large amplitude or high current density in a given location, but there's high variance, then you will not see the event. If, on the other hand, if there is a high current density value and the variance is low, then you will see the event. It's a probabilistic way to sort out of the large mass of voxels those that are most relevant for a given subject or a given experiment. In this case, we have a realistic MRI, unlike the Key Institute, that has 12,470 voxels. And I'm just scanning through this for a minute to show you the navigation tools. We know that 3 Hertz is the peak where there's most deviant, so I'm adjusting the frequency up here in the right-hand corner to 3 cycles per second. I'm also going to set some of the scaling factors here so I can look and focus in on more detail of just what I'm interested in. So right now, I'm just going to look at, this is the electrical potential on the scalp surface, and I'm just adjusting it so we get more focal view of the scalp surface. You can see the transparent scalp, that there is the brain underneath, and we got current densities of the brain underneath that we can also adjust. So for now, what I can do is slice through this, but initially what I want to do is adjust now the current source density scale. So we, again, focus on just the epileptic discharges, and I'm making it the threshold shift so one can see the extent to which there is very large amplitude events. I'm going to jump to the maximum, which is the left fusiform gyrus. Telluric atlas minus X is minus 35, Y is 55, minus 55, and Z is minus 17. You can also see those same values up here, or jump to the absolute extreme. And we can, of course, navigate. Now we can look with this using slicing tools, so we can go into greater detail of what is going on here. In order to do that, I'm going to activate the settings. I'm going to make the scalp map transparent. So transparency is now at 100%. And now we just have the brain. And now let's navigate through this rendered MRI. This is the inverse solution from the EEG scalp electrodes was used using the boundary element method, which gives you really fairly high accuracy, and it's SW Loretta, which means you can go down through the cortex and look at depth as well. But initially, let's slice through this brain. I'm going to first do the axis, so you can see the axial view, the coronal view by itself, sagittal view, the volume view that we just saw, and then the foreview that we also were viewing. I'm going to use the axial, coronal, and sagittal slice tools to go through this brain. If I want to evaluate the sagittal view, I can move it this way. If I want to look at the coronal view, I can move this. And if you want to see the axial view, you can go through, use this method, this tool, and that's going up through the brain axially. Now we can also just look at the surfaces, which are both the outer surface and the inner surface, by clicking cortex and making the cortex 100% transparent. Now we just have the planes that we see up here. For example, the coronal plane here, so you can see this coronal plane is the same as that coronal plane. Or if we want to see the cortex, it's got a different orientation, but it's the same as this axial view. This is the axial view of the 4-volume, and these are the individual slices. So we can look at the axial view here, and we can look at the volume here. It's just flipped around, but that's the same view. So this is a way to navigate through the brain and identify the focus, get a better understanding of where the epileptic foci are, and you can see that it's in the temporal lobes and the inferior frontal regions, the inferior temporal regions, the fusiform left temporal gyrus. This is coming back to the occipital region, problem area 19. This is problem area 20. Problem area 37. So you can see that the focus in the anterior posterior plane, or the epileptic discharges, are quite broad, and that was one of the reasons likely that surgery was declined, or at least a decision was made not to do surgery. We can also evaluate the brain by looking at using a head model, and it allows you to see now landmarks of the scalp a little bit better. And what I'm going to do here is I'm going to make the head model 0% or transparency 0. And then I'm going to turn on the cutting tool, and then we can go through the brain. Now we have a reference of a face, essentially a rendered face, that gives us landmarks and better understanding of where, for example, you would place electrodes to really get the best recording, which is pretty deep, but it would be in this region here. You can uncover that. There's a cerebellum. We don't have any inverse solutions for the cerebellum, but because of its nature of its lack of dipole synchrony with large masses, unlike the neocortex. We can look at the different aspects of this cutting tool. For example, I can just look at the left. Or can look at the right or the back of the head. These are just different ways to navigate through the brain to be able to evaluate a given neurological event or any event that has a focal nature to it. And we can also turn on center voxels. You can actually see this is the center of each Brodmann area that's in the brain. If we were to look at networks and just look at, let's say, the anxiety network, then the center voxels just of the anxiety network would show up. This is the default network, the executive network, etc. So you can see these different aspects for this patient for both sides and see which regions seem to be affected, or which types of functions based upon these networks here are based upon functional MRI, PET scans, several thousand of them because of the Human Brain Mapping Program, with a few $1 billion dedicated. When I was at the National Institutes of Health, I was a 128 channel EEG recording manager, I was in charge of the program, and we integrated EEG, 128 channel EEG, 19 channel, 32, 64, 256, with functional MRI and PET scans. And over the years, these different networks were studied and confirmed using these different imaging modalities. Here we can show the Brodmann area outlines. The white this is the Brodmann area of the memory system. Here's language. You can see that language must be impacted by the events, because these Brodmann areas, the center of the Brodmann areas, are really related to the left temporal lobe, as you can see here. So we can also do a movie if we wanted, which I'm not going to do at this moment. And then, of course, you can save the files. All of this information can be saved. You can actually save a file for neurofeedback. And if you want to get this back into range, to save this, to put it into a Word document, you just right mouse click and then copy image. You can right mouse click and copy the information that's in this section over here, which gives you the coordinates and magnitude, etc. And you can then paste that into a Word document for your clinic report. You can also, of course, evaluate the all slices that shows you the depth of this event. You can see the epileptic discharges are quite deep, but not superficial. By the time you get to this coordinate system here, they're virtually at this higher level. There's no epileptic discharge. It's primarily in the lower slices, and here's the telluric atlas coordinate and the Brodmann areas as you navigate through this value or this space. So that's it. This is a way to evaluate neurological events, gross pathologies, strokes, tumors, epilepsy, with a raw score. You could use Z-scores too, of course, but it's very useful in general to have a tool like this to give you as much accuracy as this does. We also can drill down. I'm going to make the cortex zero transparent and just show that that we can drill down. Now we see the whole cortex. We can go from the surface. Here, I'm going to go down a bit so we can see this epileptic event here. Right now, we're deep. I'm going to go up to the surface of the cortex. There's 10 steps. This is SW, Loretta. It's black up here because that's the dura. There's no current sources up there, but you can see there's diminished power from the epileptic focus at the very top. But as you drill down, now I'm going deeper and deeper into the cortex, and you can see that the intensity increases there. Probability values, again, it's the current density in voxels divided by the variance of the source space. This probabilistic event is much higher deep in the cortex than it is as actually in the layers of the cortex, layers 1 through 6, than it is in the very upper part of the neocortex in the left temporal lobes that we see here. So this is the example, and it's available to use by clinicians to evaluate their patients in great detail.